Well, perhaps I will be talking to you about the one of the simplest and smallest instrument of the mission. So I will be starting with some basics of the dust and big monitor, then a bit of the theory behind DIM. I'll be talking about a bit about the calibration experiments and the analysis of the detection during descent and landing, and concluding remarks. So the idea would be to make a story from the calibration experiments, then the detection, and then the analysis. So this is basically DIM. It's a small cube, 7 centimeters inside, and it's located at one of the balconies of the lander. So the aim of the monitor is to detect particles on the order of millimeters or millimetric size, moving at around 1.5 meters per second. And basically these particles come either directly from the surface or in a backfalling trajectory. So the monitor, as I told you, is quite simple. The basics behind it is the piezoelectric principle. So it's got three piezoelectric slabs on each side, and only 3 sides are active. These sides are switched on in sequence, so each side measures independently. And you may see on the table on the right, on the bottom right, some of the properties of the detector. So in total we have 70 square centimeters for the active area. So the theory behind DIM is fairly simple, and it was developed more than 100 years ago by Heinrich Hertz. So the idea is basically that given a PCT as target and a particle as a projectile, let's say with radius r and density rho, then the impact will produce an electric voltage signal derived from the mechanical stress or the deformation of the projectile and the PCT. And then we will have a pulse that will be kind of damped quasi-sinusoidal shape, as you can see on the plot. So what's important there is the amplitude that we see there in this first jump of the signal, and the contact time, which is the width of this peak. So according to the Hertz impact theory, we have that we can connect or relate the amplitude of the signal to the speed of the impact and the radius, given that we know the mechanical properties of the projectile and the PCT. We can do it as well with the contact time. That is, we can relate this contact time to the impact speed as well as the radius. And what we did in first place was a lot of calibration experiments. The experiments were quite simple, and they consist mainly in impacts of millimetric and submillimetric particles of different materials. So we try to cover basically all the possible ranges of mechanical properties that we would be expecting on the Comet. So as you can see on the plots, we tried millimetric particles of steel, rubber, glass, and LPD, which has got a similar density as water ice. So in principle, it was demonstrated that the sensor was more or less stable, and we also explored in which the signal was more or less stable as well. So in that plot, what you see is just a comparison of the experimental data and the expected theoretical data. So the question is, the former experiments were done basically at room temperature, but we needed to drop down the temperature. So we built a sealed chamber to perform experiments at minus 30 degrees Celsius, more or less. We could even go down to minus 40. So the box is quite simple, but it was kind of a headache to produce the ice particles. So what you see there is a styrofoam box. And then we have it cooled down by this copper coil, where we have liquid nitrogen running. And then the tricky part there, and not very comfortable part, is that we have to sit the monitor inside this box and manipulate it with globes, which was not very nice. But we have this mount, and we could modify the height, and we could modify also the impact angle. So that gave us important data. So as I said, dealing or handling ice particles was a headache, and in principle we kind of broke our heads just to define how to produce particles. In the end, we produced them very easily with a pipette and just cooling individual droplets on one of the plates inside the box. So there are the particles we use. They are fairly spherical. You may see the scale, so we have more or less control of the sizes. And these are, of course, simple water ice particles. And then the idea was precisely to produce these curves that related these two amounts, that is the contact time and the amplitude. And there you see that we have some deviations with respect to the expected theoretical behavior, but in principle we have a more or less a stable performance. And another important thing was to calculate the detection range of the sensor. So this is basically what we have. Of course, this is considering that we have a range of more or less stable signals. It doesn't mean that we cannot go further than 1.5 meters per second or less than 0.1 meters per second. Of course, in those ends we have a lot of noise, and it's difficult to tell what is a real signal and what is noise. So let's go to the detection during descent and landing. So in total, DIM registered a lot of events, but only 13 events that could be considered candidate impacts. Unfortunately, out of those 13 events, only one, we are sure that it's an actual particle. So what you see there is a histogram of the detection. So the big peak you see is precisely the particle that we are for sure know that it's a particle, and the others may be actual particles, but the noise is really large. So the colors stand for the different sites on which these particles were detected. And just for reference, if you see the picture on the bottom left, is precisely the location of the monitor. If we sit behind the lander, then the Y side would be facing your left, then the X side would be facing towards the front, and the Z side upwards. So this is basically an analysis of of what we got. The question is, let me go back a bit. An interesting thing here is that we have a very long contact time and a very small amplitude. So we tried to figure out what type of material would that be, considering that at least in our calibration experiments we didn't have such behavior. So in the end we just run into aerogel particles that you may remember as part of the traps of dust in the Stardust mission. And in particular, the aerogel we used has got a density of 0.25 grams per cubic centimeter, and more or less a Young modulus, a reduced Young modulus on the order of 50 megapascals. And this is basically the type of signals that might be quite similar to the particle we detected. So this small amplitude and very long contact time. So the signal I just showed you in the previous slide corresponds to the last block of the table, but we also did experiments with other aerogel particles. For example, in the case of the signals from the previous slide, we have a more or less spherical particle, but we also used a fairly irregular and a very irregular particle, and just by chance the very irregular particle on the third part of these pictures has a very similar values as the particle we detected with DIM. So given these values, I mean the amplitude and the contact time and the equations I just presented in the second slide, sorry, then we can derive the impact speed and the radius of the particle. The tricky part here is assuming or defining what type of Young modulus we have. So based on the aerogel experiments, then we assume that the Young modulus was on the order, or at least in the range, between 50 and 500 megapascals. If we take these two values, then we have two possibilities. So what you see on the top left of the plot is the ranges of values. So we may have a particle on the order of 2 millimeters in radius and very slow speed, 0.097, or we may have a faster particle, let's say on the order of 1 millimeter in radius and 0.7 more or less in speed. The question is, the data points that we have a very fluffy particle that is with high porosity, either some regolith material or ice. We may have further information from the detection geometry. So what we have on the bottom part of the plot is the trajectory of the lander while it was approaching to the comet in comet-centric coordinates. And we have these two vectors that are basically the same in the case of the lander picture. The lander would be exactly in the position as it was during detection. That is, one vector is pointing to the sun, and the other, the red one in the lander figure, is the vector which is perpendicular to the site where the particle was detected. So the angle between these two vectors is 30 degrees, so you may have an idea of the position. So the illumination conditions for the lander is correct, but not for the other plot. We have most of the information. That is what we need to find the speed of the particle with respect to the comet is simply to do some relativity. That is, we have the speed of the particle with respect to the lander. We have the speed of the lander with respect to the comet. And then we just have to obtain directly the speed of the particle with respect to the comet. If we assume these two values, then what we obtain is this range, a range between 1 to 1.42 meters per second. Of course, if the impact is inclined and not normal, as we are assuming, then of course we would have a larger speed. But just let me point that at the detection distance, we have an escape speed on the order of 0.5 meters per second and an orbital speed of 0.36, which means that the particle likely moved in an escape trajectory and might have come from an active region of in the comet surface. So just final remarks. We made a DER analysis with noise in regards to the noisy events, and some of the particles might be, okay, if we assume that these particles are not precisely noise, but particles just masked by noise, then we would have, if we have a Young modulus of 500 megapascals, particles on the order of 0.2 millimeters moving at something between 1 and 2 meters per second. Unfortunately, no particles were detected in the final landing site. Probably we have low activity or something that was shielding the instrument. Thank you for your attention.
Okay, the paper is open for questions.
One man's noise is another man's data. I know some dust detectors are very sensitive to vibrations of the instrument of the spacecraft. Is that the case for the lander? And if so, were you able to fine-tune times of touchdowns or operation of the hammer?
Well, we may have some interference with the operation of other instruments, but also we may have some vibrations or reverberations in the PCTs. That's basically the sources of noise.